Um, yeah. So today I'm going to be talking about project process injection, at least using Ptrace, and how you can have fun with it. I guess. Um, just a disclaimer: this is, I would say, a little bit of a difficult topic because you kind of need to understand the Linux process and how it works and all of that fancy stuff. A little bit of assembly and a little bit of how the memory works. I'm still learning part of this, so like I started this at the beginning of this week, so um, some of the topics were also flying over my head. So just a disclaimer. So I'm just going to quickly talk about like what a process is, then go into process injection and Ptrace and all the stuff. So what is a process? I guess you guys probably know, at least if you've done the competitions, you've done the PS-FAUX or whatever, and you've seen this kind of graph, not graph, but like a table of things running on your system. That's pretty much what those is. A process is just an instance of a running program, and you can have multiple, or a program can create multiple process. So think of threads in Python, if that makes it easier for you. Just an interesting fact, the maximum that a process number can go to is 332,767. And when it gets to that number, it just resets back to a lower number, but not zero because, well, not zero and one, because one is system D. So that's the parent process. Everything comes from system D. But after it reaches 300, that number, it just picks a number that's not like a process number that's not being used. So just an interesting fact. So in Linux, when you run a process, it creates a file for you, and it's saved in the /procs folder, and the PID is just going to be that number. Inside of that folder, you have a bunch of information about that process. So, for example, if you want to see the memory, the loaded libraries, or you want to see the command line or stuff like that, it's going to show you. This is just an example of a process 6749. This is all the process information you get. Some of them you need to have root to read them. For example, the maps. That's something I was working with a lot. So with that, you have to be root to be able to read that information. This is just a quick description of like some of those information you can get. The fun ones I would say is the CMD line that just shows you what's being in that command line at that time. The CWD just tells you where that process is in the file system. It's a symlink, so it's not like going to be exactly where it is. So it's a fun thing to just play around. For anyone that likes to play with the Linux stuff, if you find someone else on your machine and you find the process ID of that bash, if it's bash shell or whatever, if you go to the /proc and that PID and go to FD, which is file descriptor, you can echo whatever into the one, which is the standard in, and that just messes with the terminal. So that's a fun trick you guys can do with your friends. So what is process injection? Using some definition online, it is a method of injecting random code in a specific address space, and your process is different from the target process. This can be used to access process memories, network resources, and potentially, if you, for instance, do a process injection on a root process, you can possibly change your permissions to be root. So this whole research project for me was to learn how to inject into the SSH process and attempt to grab the user's password and save that to a text file. So there are different types and for different operating systems. For the Windows folks, there are a lot, but this is a few I picked up. I know the main one people use is a DLL injection. So if you're interested in doing any of those Windows stuff, that's things you can look into. For Mac OS, it is there. The only one I know of is the dylib injection. So it's just inject into a library, stuff like that. I might give a talk about that depending on how time permits. Um, and you can also inject into third-party frameworks. Again, that's a topic for later. But for this talk, we are going to talk about Ptrace, which is a debugging mechanism in Linux. There's also syscall. Just the way syscall is used mostly is in rootkits. You just hijack that syscall and put whatever code you want in there and continue the process. So, like I said, there are multiple ways. I believe there's two. So there is the user land and kernel land. The easier way is using the user land, which is, in my case, using Ptrace. Again, I think there's more, but I couldn't find it. Maybe it's one of those obscure methods. Then if you go to the kernel side, I'm 90% sure there is something there. But again, it's probably like techniques that are really obscure and people don't really know about. So I believe there's some crazy stuff out there you just don't know about. I did find this PDF. It was created by Mendian, and it talks about the kernel and the user land ways of injection in Windows. So that's for the Windows folks, I guess. So what is Ptrace? Ptrace is a system call that provides a means to gives a process, so a tracer, the ability to observe and control the execution of another process. Again, the easier way to think about this is when you're debugging your code. When you put like the red dot on whatever line you're trying to debug and it stops, that's the whole process is like that. You're controlling the memory and all of that stuff of another process. Again, for Windows, folks, these are the things you would use if you're doing process injection. You can look into the memory, try to write to the process memory or read that process memory, blah, blah, blah. So all of those fun stuff is what you would use. So some of the uses for Ptrace or just process injection can be if you're debugging, like I said, we use that for CS1, CS2, and if you're a constant tool developer, you definitely have to debug your code. So if you do a lot of GDB or radar or whatever people call it, that stuff like that. I know CTF folks definitely do that for reverse engineering. You can also use that to like patch a program. Let's say a program is a company is taking their time to update a specific program, but you need it fixed, so you can just do like a quick patch using Ptrace to find whatever function and just try to bypass it. So there are multiple ways for or multiple use for Ptrace, but this is some of what I have. Ptrace has some options for you or operations that you can do. The main ones that most people use or I used are the Ptrace attach. I mean, based on the name, it's pretty straightforward. It's just attach one process to another. So I can, and it also pauses that process. So in that state, it's just stuck, and from there I can do whatever, like read memory and do all of that stuff. The next is the pick test text, which allows the process to read the memory. So again, pretty straightforward. And the poke is to write memory. You can also get the registers. So if you're trying to look into the assembly part of stuff, so if you want to find the RIP, the RAX, RBX, and all of that fancy assembly operation, you can use the get regs to get those information. And if you're trying to edit that stuff, you can just use the set regs to do so. After you've done all of that and you want to resume the process, you just do the Ptrace _ continue. Well, that's how you say it, that's how you write it. But essentially, it just resumes that process. So we're going to take this and apply it to the SSH part of the stuff. So the goal here is to attach to the process, examine the part of the process we want to inject to, and just make it continue. So first we attach by using, again, the ptrace attach. And what you have to pass it is the PID, so the process ID for the SSH process. You pass that, and this will send the sig stop. Again, this is used for debugging. If you really want to understand all of this, there's always the source code to dive into. So that's how you would attach to that to the SSH process. Then next, I want to get like the registers and all of the information at where that process stops, just in case, because I'm going to have to modify those informations, and after I've done all my modifications, I need to replace it back so that the process doesn't just die. So just for safety, I use the get regs to get all of those information. You can also find like the, okay, before I even talk about that. For the SSH experiment, I'm trying to find a place where I can inject my code. So we have to find a specific place in memory in that SSH process where I can inject into. A way you can do that directly from the command line is just, again, going to the process and the /procs PID. And if you cat the maps, it's going to show you an example like this. And here you can see all of the attached, libraries that the process is using. In this case, our target library, library is the not libc, sorry, is somewhere at the bottom, but yeah. Also, we are looking for the RXP, the ones with the X, which X means I can execute it in that part of memory. So that's an important thing to look for if you're trying to execute code. So just like before, we made a copy of the text part. Now we have to make a copy of the data part. Usually, at least for me, it was just a bunch of zeros, so there was nothing in that part of memory. So I decided to just write to that specific part. I found out there's multiple ways to read the memory. There is the process _VM _read v. This is something I learned, and I think I want to look into this like after this presentation to see exactly how it presents this information. And finally, when I'm done with all of that, we can make that we can overwrite that part of memory. So like I said, we put in the PID, the process ID, the address that we want to edit, and the word is just what I'm trying to put into that part of memory. And once we have all of that done, again, the last edit we have to do is just change the RIP, which stands for, I don't remember, but it tells the CPU like what the next, it tells you like where the next line to go to in the command line or in the process. Go to reversing and select 202 to understand what that meant. After I've done all the editing and I've updated the RIP to point to the injected code, again, this would be the address of where we want it to go. We use the set regs to just save everything, and after that, we just continue that process. And it would resume like everything is normal. So now we've gotten to that part, we need to find the specific place in the SSH source where we want to grab the password. So we had to find like a signature that makes so there's a bunch of functions. The ones I am looking into is auth _password. That's where your password goes through in plain text. So I had to find the assembly that makes this function unique. So in this case, it is the compare RAX 400. That 400 is the 10204. That's the maximum password length. So just also a quick fact, you can have a password of 1,000 and 24 characters long if you want to, but that's the max. So after finding this place in memory, we just have to do some shellcode shenanigans to inject or to replace that part with our own code. So to load our code into that SSHD, we're going to need a little stub to open our malicious library, which I will talk later on in the future. So again, the library that would do so is the libdl. In this, there is a function called the dlopen, and this allows you to open a shared library inside of a process. So we're going to inject into, or we're going to use the dlopen to load our malicious library that would perform that hooking part of the experiment, so the part that actually grabs the password. And like I said, the dlopen is just a dynamic link call, which you pass in the shared library path, and it just does the magic it does and opens that or loads that library for you in that calling process. And lucky for us, that the libdl library is already used by SSH, so there was no need to do some other like magic to get this loaded in memory. So it's already there. It makes it so much easier. So before we even find the dlopen function, just due to like modern solutions to all of these attacks, there is something called ASLR, which is just random. The address of a function is different every time it's being loaded, so it's not going to be the same all the time. So in order to like find that function address, we have to do a little bit of math, and it's pretty easy. We just do a difference between the libdl base address and the function, and we can just find the offsets, and that tells us exactly where it is in memory. Sounds weird, but this is the math that does it, and it just works. I'm not going to question it. So after we've So after we find that memory of the dlopen, we need to pass it the path of our malicious shell library. So we have to write into that process. And like I said, the poke text is going to do so. We pass it the PID, the address, and the malicious whatever payload. In this case, it's going to be the path of the shared library. And as you can see, the shared library is going to be saved in /temp, and and it's going to be written into that address. Yep. And again, after you've done all of that, you just need to reset some stuff. So you have to point the RIP, RAX, and all of that stuff to your malicious part in memories and resume the process, and it should just work after that. The problem is mine did not work. So I got to that point in the research, and I was like, oh, I kind of understand what's going on. Then it just stops working. I still have not figured out what the problem is, but there is like sample code, so I can just show you what it's supposed to look like. And also, I didn't have a lot of time to like really do a lot of debugging, but it is what it is. But if things were to work well, I would have to write a little bit of shellcode, which will grab, as you can see, it says password hook right there. So that would be the part where I actually overwrite sorry, I'm just gonna go back a little bit, where I override this part, the compare, and grab the password. But again, my knowledge did not get to that level, but there's a blog post that you guys can read if you really want to know what's going on. But I will show you what my code looks like when I ran it and what the code looks like. And then I'll show you a video of the actual project working like fully. So let's do that. Okay. second. Okay, I guess you guys can see that. Just to read a little bit of code. As you can see, I started by, I didn't even attach the process first. I was trying to find the address of the dlopen, and this is where I did the fancy math. Oh, where is it? It was right there at the bottom, to find the exact part in memory. This is just me doing some precaution stuff. It doesn't really, it's not necessary for now. But this is the main function, the inject SSHD, which is right here. As you can see, I found the process of the SSHD, then I try to attach to it, grab the information just as a precaution, save that in another part of my process, and I try to change it and point to our malicious part. So the /temp inject SO would have been the malicious library that actually grabs the password, and we did some padding just in case we might overwrite some stuff. We just did some padding for that. And if things worked well, we would have been able to inject our library at a specific address. But that's where my project stops. It broke around in this if statement. I actually got here. So I'm just going to run this so you guys can see. Oh, that's small. One second. For some reason, I don't know how to increase the. Oh, it's right here. Never mind. Okay, that's good enough. So I'm just going to compile my code again. Ignore the errors. As you can see, it was able to find. I'll just use my computer. It was able to find the process and find some find the dlopen address. So it's the dl function is located at this point in memory. So this is just me just trying to see the information before I erase it. So this was the initial RIP and all the other stuff. And after that, I would have injected my code. I should have put this. Injected code should be at this part in memory, and then I pointed to that part. And at this point, it should just continue the process as normal. But apparently, the SSH process just dies. I can show you what the actual error is, which we can just find by looking in the log files. So 1 second. So as you can see right there, there is a general protection at this address. I don't know what that means, but that's something I have to figure out. But this is where I'm getting stuck at. So that's my problem. But I can show you what the original video which would look like if everything works normally. So I'm just going to zoom in here. So is that good? I'll zoom a little bit closer. Okay. This guy is using Vagrant, which we're going to have a talk about in the future. It's just a way of managing your VMs without using the VM GUI. It's so much better. In this case, he has more scripts, but as you can see, he's attaching to a process 1592, which is the SSH. And he has another one where he logs in using test user and some random password. And if things were to work perfectly, it should just, SSH should look normal and nothing should break. So blah, blah, blah. He tries the password one last time. So, okay. And all the passwords are saved at 1 second. So everything works perfectly. He was able to find the SSH process, then find the child process that was spawned when a user SSH into that. Then he does some injection. It worked perfectly, and he was able to grab the password, and he saves all of them at the /temp SSH password. And as you can see, this would have been the results if everything worked perfectly. So this was supposed to be the goal of the project. Again, I didn't get to this part, but yeah. So for me, what did I learn during this process? Oh, first of all, I just found out my love for C came back again. I know it's crazy. I didn't know. Just writing C is pretty fun. I mean, you hate yourself, but you love it at the same time. But apart from that, I got to understand like a little bit of how the process memory works and the process allocation and what a process is and all of that, just information about it. And also how to like change those stuff, like the Ptrace and getting like the address in memory and trying to change that to where I wanted to go to. I learned a lot about that. But I do think that as I go on and just continue working on this, I will learn more, like trying to debug much larger programs. Like, again, SSH is a huge one, has a lot of functions. It's really hard to find like a specific part you're looking for. So that's something I'm going to keep learning. And also writing shellcode. I didn't think I was going to learn shellcode anytime soon, but I think with this project, it's probably going to force me to do so. So I'm excited about that. And again, the main part is memory. I feel like if you understand how memory works, at least in any operating system, you can do a lot of damage. I know specifically in the Mac OS field, a lot of the bugs is just memory stuff. So if you know how to play with that and change it and exploit it to your own doing, I think you can find some really fun stuff as you do so. Yeah, so that's again, this is just not me coming up with some new idea. I actually read that first blog post. So that first blog post would say everything I just did, but like actually explain it. Hopefully you understand that better. The code sample is the second link. So if you want to read the C code and everything else and see how it works, you can also just do that. And the other ones is just Ptrace and just some links to some things that were useful to me. The last one is a Linux programming interface. It's like C programming, but for Linux. It's not too low level, but I think it's good enough for someone who is really interested in learning like the Linux kernel and just how things work. So that's all I got. So yeah, see you guys next week.
Wow. Some hot stuff right there from Emmanuel. Okay, next up, we're going to have Philo with Freaking and the History of Hacking. Give a round of applause.